Welcome to my home. Today we're going to talk a little bit about how I go about finding meteorites and identifying them and what they are and how you photograph them and all that kind of thing. Let's start a little bit with some definitions. First of all, what's a meteorite? So a meteorite is just a chunk of stuff out in space that falls through our Earth's atmosphere and survives, something that hits the ground. And these come in various types. There's the iron meteorites, which are almost pure iron. There's a little bit of nickel and some other things in them. Then there's the stony iron, which is a mixture of iron and rock. It's usually big crystals, so they're quite beautiful objects. And then stony meteorites, which are just like rocks that you sort of find around here. They have some different things in them that we can use to tell them apart from Earth rocks. And most of these things are highly magnetic, which is not what happens with most Earth rocks. I mean, there is magnetite and goethite and lodestone, things like that, that are highly magnetic on Earth, but not many. Okay, most of them oxidize because of oxygen and rust, and so they become non-magnetic. Okay, so those are some definitions. A little bit about falling through. When we talk about things like meteorites, we're talking about things that fall through at 25 to maybe 100,000 miles an hour. So they're really moving through, and they're falling through for about 3 to 8 seconds. And they're only visible when you see them in the sky. They're only visible for the first half, roughly, as they come through from 120 miles up down to about 50 miles. And then at that point, they reach what's called terminal velocity, which means they're not picking up speed anymore. They're going the same speed all the way through. And so they cool down enough that they don't give off light. All right. Most meteorites, when they hit, are cool. And you might think, wow, everything I see, Superman, when he comes out of his little spacecraft, it's steaming hot. Basically, what happened, though, you're up in space and you're 3 degrees Kelvin. That's like minus 400 and something Fahrenheit. Incredibly cold. And then you heat it up for 3 to 8 seconds and you hit the ground. Well, and the other thing is not only are you heated up for a very short period of time, but a lot of the stuff on the outside that's heated the fastest is melted off, and that's called ablation, okay? Taking the heat away, sort of like boiling water. When you boil water, the steam takes the heat away. When you put a thermometer in boiling water, it's never over 212 Fahrenheit, right? Until you evaporate all that water away, boil it off. So the steam is where the energy is taken away, and the ablation takes the heat away, so the rock itself stays relatively cool. So in the middle of summer, if you see something land in a pile of rocks from out in space, you go over quickly and find the one that's cooler. It's not going to be cold, but it's going to be cooler in most cases, okay? If it's got a lot of iron in it, it could heat up like a pan, it could heat up quickly. All right? So at this point, I'll show you some pictures of meteorites and a little sheet that I wrote up, and you can look at that for a few seconds. Okay, we're back. Let's talk a little about the micrometeorites now. The only difference really is the size. These things are tiny, okay? Most of them are between 100 and 500 microns. A hair is 80 microns. So you're talking about something that's just a little bigger than the width of your hair. So the size of a tiny sand grain, okay? And I'll show you some pictures in a minute that will give you an idea how big that is. So, like the meteorites, they're objects that hit the ground after falling through the atmosphere. And again, it takes about 3 to 8 seconds. Even though these things are tiny, you think they'd be, floating down. They're not. They're moving at high speed. These are tiny, so they can really get moving. They could go 25 to about 150,000 miles an hour. Okay? And so and because of their size, they can involve friction. Okay, friction is a big element. So when you rub your hands together, you feel them warming up. That's the kind of thing that's acting on them, as well as something called ram pressure. When you push something and you get push it against air, you're building up pressure. If you pump up a tire on your car and feel it, you'll feel it get warm. And if you let the air out of your tire, you feel it's cold. So it's like pumping up the tire, building up the pressure and heating things up. And that's what heats up meteorites. And it also somewhat heats up micrometeorites. The friction is more of an issue with micrometeorites. Okay, and so this heating is really important in terms of identifying micrometeorites. There are some that are completely melted, and those are called vitreous or glassy. And there are some that are not heated up at all, almost, and they're hardly heated, and they're called unmelted. Surprise. And it's basically got to do with how they hit the Earth. If you're thinking of the Earth looking down on the North Pole, thinking of the Earth going around, if you're going with the Earth, you're falling in this direction, you're hardly heated up at all. If you're falling in the middle, you're heated up moderately. And if you're going against the turn of the Earth, you're going to be hitting that atmosphere really hard. Think of I hate to use it, but a car crash. If you're behind someone going in the same direction and you hit them, it's just a little tap. But if you're going in opposite directions, it could be quite dangerous, quite deadly. All right, so the same kind of thing. I want to stop here and show you a graphic of that so you get an idea what we're talking about. Okay, we're back again. So we talked about the different kinds of micrometeorites, and basically they go from unmelted all the way up, okay? So we have the unmelted, which are incredibly hard for us to identify. We have something called scoriaceous. I don't know if you've ever heard of a volcanic rock found near volcanoes called scoria. It's got lots of holes through it. And that's basically what scoriaceous means. It's got whole vesicles, they're called, where gas bubbles burst and make these little holes in it. So that's one thing that can happen. The next one up is porphyritic, where the crystals that were in the rock itself as it's falling through are hardly melted, but there's some parts of it that are melted into a glass. And so you've got this glassy stuff with these big crystals poking out, and that's called porphyritic. Porphyritic means you've got big particles in a very fine-grained background matrix. Okay, and then it goes on to barred olivine. And olivine is a mineral that can take high temperatures, so it doesn't melt easily. Okay, and so you get these crystals in there that can form plates, and those plates end up in layers, and those are called barred olivines, okay, when they're in layers. Then you go where the olivine gets partially melted and then recrystallized. And by the way, those barred olivines are ones that we can identify easily. The porphyritic we can identify. The barred olivines have interesting flight structures on it. And I'll show you a picture in a minute. And then the cryptocrystalline is where it's melted quite a bit and recrystallizes. So you get these little crystals growing of the olivine in the matrix, okay? And it forms some interesting things. Sometimes they have big bumps on the outside, and that's called a turtle back because they look like the scales on the turtle's back. It's big lumps sticking up. And then the last form, as I said, were the vitreous or the glass at the far end where they're completely melted. Those, I think, are very difficult to find. I haven't found one yet. And you really need to find a piece of metal bead sticking out that you can identify so that you know that this thing is not from around Earth. There's so many things here that can be made on Earth by humans that look just like micrometeorites. So it's a really hard thing for some of these to be able to identify. All right, so let me show you some pictures of these different things. I'm going to show you a temperature graph that shows the different things, and then I'm going to show you individual pictures of the ones I described, and you can see what those look like. Okay, so we're back. I wanted to talk a little about how we go about searching for them. Up until 2016, there wasn't a protocol for being able to find these things in cities. They had obviously been found in Antarctica, where there are almost no humans. Some deserts, like the Atacama Desert, which has very little human activity, they found some there. And deep oceans, they found some. But up until now, we haven't found ones that were landed on Earth recently, right? You think about Antarctica and oceans and deserts. Those have been sitting there for thousands and thousands of years. But the ones that lands on your roof, I mean, like on my roof when I found mine, my gutters hadn't been up for 10 years. And so, you know, it's less than 10 years old. And there's some that the World Authority, Jon Wallace in Norway, came up with these protocols. He studied it about probably now 20 years ago. He started looking when he had one fall on a white tablecloth at his house, and he saw this little object, and he took it back and looked at it, and he got hooked and started, and now he's found thousands and thousands and thousands of them. He's got a website, by the way, Project Stardust, which is a great website. You ought to check it out if you're interested in this. It's a Facebook page, and he has pictures all the time. So anyways, so we're talking about micrometeorites and how you find them. Well, it turns out micrometeorites hit the Earth more often than all the other meteorites combined. I'll show you a graphic in just a moment that shows this huge peak on a graph showing the mass of material that hits the Earth from microscopic particles. Anything less than about 50 microns get burned up in the atmosphere. So you're looking at this curve starting at about 50 microns and going up and up and up and up. And then about 300 microns, it turns around and it comes down to about half a millimeter. So you're talking about tiny, tiny little things in this huge peak. And that huge peak represents about 60 tons of material a day. It sounds like we ought to be swimming in this stuff, right? But remember, the Earth is tremendously large. And so that comes out to about 1 meter by 1 meter. That's 3 feet by 3 feet. 1 micrometeorite per year per square yard, if you will. And so that's not many, right? So you're going to have to really look to find these things, even though there's tons and tons of it. The other peak that goes along, there's a little peak at about a centimeter, half an inch size, you know, so little handheld meteorite. Those are the ones that I collect and can afford. And so those, and then there's another one at the end where it curves way up at the end. Those are the ones that are tremendously large. The big ones, like the one that hit Chelyabinsk a few years back, and the one that fell through Maine and was never found, but it fell into Maine in 2016. All right, so I'm going to show you some graphics, that graph with the big peak and stuff, and take a look at it and make sure you understand that a little bit, because it's going to impact how we go to look for these things. So I think the next thing we should talk about is how you go about finding these things. We'll talk about how to identify them in a minute, but let's talk about how you go about finding them, because that's the first business. The first thing I do is try and find a nice big flat roof. That's the ideal, right? Where nobody is on it and it hasn't been touched for years and years and years, right? Because if we're looking for something that only one for every square yard, it's going to take a very long time to find. But if you have something that hasn't been touched for 30 years, you're going to have 30 particles in that square yard. Yippee! Now, maybe we'll find something. It's a heck of a lot easier to find something like that. Gutters are okay as well, as long as, you can pick the material out and stuff. The problem with gutters with normal, roof shingles is that much of the material in roof shingles is magnetic and stuff, and we'll talk about why that's important. And they're dark too, so they look very much like stuff that might be a micrometeorite. They're not, but you got to take some time to look through it. All right, so the first thing you need is flat roof. Second thing, a strong magnet. Okay, I have a neodymium magnet. Let me just grab mine over here, right here. And this is a fishing magnet, so it's got a 165-pound pull. You'll notice I got it in a bag, and I sealed this bag. That's so the particles can't get in here. This magnet is really strong. If something gets stuck to it, it's really hard to get off. And then I always stick it in a second bag, and that way when I'm looking for stuff, I can pull it really tight so it's nice and flat. And then when I go looking for stuff, it gets stuck on the outside. I put it in another bigger bag, pull my magnet out. Oh, there it is. And the stuff falls off into the other bag that I'm collecting. And then I go back and do it again and again and again. And I'm going to show you some pictures of that kind of stuff in just a moment. All right, so that's the second thing. Next thing, if you can get a dry roof, really bone dry, that's the best, because then you can sweep all the material up, take your magnet and run it through, and you don't have to take everything home and try and clean it all up. Okay, so you take that material, you get it in a big bag, and you take it home. Then you take some dry powdered laundry detergent, a little bit, in a 5-gallon bucket, stuff your stuff in there, and wash it thoroughly. Let it settle a little bit. These particles do take a few seconds to settle, and then pour off the junk. We don't want any of the leaves and garbage like that. And keep doing it until it comes out clear, right? And then at the bottom, you've got some stuff that you can look at. And what I like to do is dry that completely. Take and pour it onto a plate if I can, a big white plate or something, or something flat that you can spread it out on. And just let it dry until it gets bone dry. I like to then put it through some sieves. And I have some pictures of that, which I'll show you in just a moment. But you can use just a window screen. Anything smaller than a window screen is worth looking at. But if it's bigger than window screen, you're not going to find anything. That's too big. So you'll see that as a simple way of searching. Some of the really small stuff, it would be nice if you could remove that too. But getting some of these sieves costs some big bucks. I have a set, and it probably cost me a few $100. So it's up to you if you want to buy something like that. But most of these things are going to be found between about 200 and 400 microns. That's the normal range. So if you get a screen set, no larger, nothing smaller than 100 microns is worthwhile, and nothing bigger than about 500 is really going to be useful. I've never found, well, I found one that was bigger. So it's possible to get them bigger, but certainly never over a millimeter for normal people. I mean, Jon Larson has just found 2 or 3 but they're incredibly rare to find something that big. Okay. All right. I think at this point we'll pause and let you look at the pictures that I have. So you'll be looking at pictures of some of the equipment and stuff that I use to find stuff on the roof and what it looks like. All right, so we're back. One thing I forgot to mention, when you're up on a roof and when you're washing this stuff, remember there's all kinds of stuff that's on a roof. Birds do their business and stuff like that. I had one sample once where it was moist and it was just absolutely foul. And I would recommend you not putting your hand in something like that. So I always bring like Playtex gloves, really thick, nice gloves, and I don't touch this stuff before I wash it thoroughly and get all that junk out, because it's pretty nasty. And if you're really worried about it, if it's really foul, I have poured in alcohol, rubbing alcohol for a day or two, and let's just let it soak, because that kills most things. All right. So after you've cleaned it and dried it and you've sieved it so it's all ready to go, then we're ready to look through the microscopes. Okay. And I usually like using a low power microscope to start and try and pick out things that look promising. I can't tell what they are at that point, but I can see things that have certain characteristics. I want something that's roundish, but not necessarily perfectly round. If it's a glassy thing, it could be perfectly round, but the barred olivines and the porphyritics and things like that, they're almost never perfectly round, cryptocrystalline. So you want things that are a little bit off, not quite, and usually these things are dark. They're covered in a mineral called wustite, which is a highly magnetic iron oxide that coats these things, and it also is very resistant to erosion. So we've found micrometeorites in fossils that go back hundreds of millions of years. So it's pretty amazing. So when we're looking, we start with a low power microscope, and we're looking at a tray full of stuff that's small sand size. And you're looking through particle after particle, trying to pick things out. I use a fine paintbrush, and I'll show you this stuff in just a minute. And then once you find stuff, then you put it under a high power microscope, and then you try and figure out if it's something worth taking a picture at that point. So let me stop here. We'll take a look at some images that I've shot of my microscopes, and then we'll actually look at the microscopes and do a little bit talking about that. All right, hold on. Okay, so we're back. This is a sample. You can see they're pretty darn small, the particles. This is the little petri dish I used that you saw in the picture. And then here is the low power microscope. It's a zoom, so you can change the magnification and you can focus there. And then the tray goes under here, and then I have these little gem jars, and I use my little paintbrush right there. Let's see if I can get it in focus. It's a little paintbrush, and I grab the item and dump it in those little gem jars. If you want to be really careful too, you can dip a wooden stick in some water and then touch the object, and it sticks by surface tension. Okay, so you start by looking through there, and you saw some images of what that might look like. I did show an image of real micrometeorite in there, and you may or may not have even seen it. So it's a difficult process, but you get used to it. And then here's my high power microscope, and we're looking at over 200 power, and then we have different lights that I can bring up to try and get the lighting just right. At this point, I want to talk a little bit about how we capture images. Up on top here is a camera that is used for my microscope. It's a 10 megapixel camera, and it hooks up to the laptop. And so what I do is I focus through, and I use a type of photography called focus stacking. So I think at this point, I'll show you a little thing on that. It's a little write-up that I wrote about it and a picture set, and you can get an idea. what that's like. Basically what you're doing is you're shooting a whole bunch of pictures. As you look through a microscope, a high power microscope, you remember that only thin sections of the object you're looking at are in focus. All the rest is out of focus, right? High power means really thin depth of field. And so as you focus up and down, you see different parts. Well, with this thing, if I take lots and lots of images, I generally take 200 to 400 images of the same object at different focuses. So we're building it up, each slice, and then I run those images, 200 to 400 images, through a special program. I get something that comes out with all the parts that are in focus put into one picture that comes out as perfect as it can get with the images I provide. That's called focus stacking. So take a look at the images that I have next, and you'll see some examples of that, and I hope that brings it more into focus. Okay, now that we've talked a little bit about the camera feeding to the computer here, I want to show you a little bit about what I'm going to be doing. So I've got this microscope slide under the microscope being lit up like crazy. I have this stepper motor over here that actually controls the focus knob and can be controlled so that it can do tiny, tiny little turns using this device here, which is called a stack shot. And we're doing 3 micron increments according to that stepper motor. So we're doing tiny little turns on that. And I'm going to set the start and end position. And this is what it looks like on the screen. And you can see this thing that looks really kind of cool. I mean, it's got these feathery things here that look like little feathers. And you'd say, wow, that must be one. But I can guarantee that's not one. It's something we call an I-type. There is an I-type that is an extraterrestrial, but almost all I-types that we find in cities are man-made. And so this is some kind of man-made thing, but I thought it was a pretty thing, so I figured we'd try it. So this is, you can notice that the whole thing is not in focus. Right now I'm going to focus on the very tip of it. Right about there is where I'm going to start. So I have a little bit of overlap, and then I'm going to bring up the capture program because I want to pick the file it goes to. I already made one, so I called it Feathery Eye. Okay, and we're going to do, change that to 3 microns. And we'll call that Feathery Eye. And it's row 9, number 5. Okay, so that's set to go. Let me focus the back end, and you notice parts will come out as it comes through. You see it getting in focus, different parts, and the top is now gone, but the sides are in focus. And so we're going to take a bunch of images all the way down to the bottom. So we're trying to get to the bottom. And that looks like it's got just about everything. We'll say that's good. And so I need 290 images. So let me type 290 and we'll say go. So we just took one image. There it goes. All right. So I'll come back when it's done. So we're about halfway through. Takes a lot longer to go down the sides than it does across the top. So there we are. You can see it looks totally different than when we started, and there's the numbers. Okay, so we got another 100 or so to go. Okay, so I've downloaded all the images and highlighted the ones I want. There's 280 final ones. I'm dragging it into this program here, which is a stacking program. I'm going to go up and hit stack and align and stack. And what it'll do, it'll show the picture I'm looking at here and the final picture over here. Okay, and I'll let this run for a moment. You'll see it's going through little increments. Can't see much at this point, so I'll come back when a little more is done. Okay, we're almost done. Coming to the end, you can see this is the image that we're looking at the very top. And it's adding that to this final image. And I'll show you when it's done. Okay, so there it is. We're going to get out of this program. Here's the image. We're going to go into a type of Photoshop just to crop it and stuff like that. So I need to find it. It's in there. We'll crop it. And I'll finish doing some stuff to it. And I'll show you what it looks like at the end. So here's the final image after the Photoshop stuff. It didn't do a whole lot. It just cropped it and changed the lighting a little bit to bring out some of the features. I wanted to show you, I ran it through another program called Topaz Denoise, and look at the difference in the sharpness. It's incredible. So I'm going to zoom way in. Let's go like that. That's what this one looks like. All right, and then we'll go on to this one and do the same thing, and look at the difference in the sharpness. You can see each of the individual crystals in here in sharp relief. So incredible. So this is what it looks like, and you know, it's metallic for sure, you can tell, and it's got those great feathery features, but it is not a micrometeorite. Okay, just to wrap up, hopefully this has given you an introduction to micrometeorites. If you think you found one, if you try it and think you found one, the best place to go is Jon Wallace's site. It's called Project Stardust. It's a Facebook page. And you can get his book at Amazon. It's called In Search of Stardust. It's less than $10, and it's got lots of pictures. One of the things I want to warn you against is going on YouTube. Many people have shown me pictures from YouTube or talked to me about things they've seen on YouTube. And on YouTube, you can find people who believe that any round sphere you find in a sample is a micrometeorite, and that is just wrong. If that were true, I'd have hundreds of thousands of micrometeorites, and right now I only have 28. So it's not an easy process, I understand that, but every little sphere you find is probably man-made or human-made. So, you know, fireworks, welding, all kinds of stuff. When you're on a big roof, welding is all over the place. There's little glass spheres created there. There's all kinds of junk in the air, and these particles can be picked up by the wind quite easily. So it's interesting. I think it's fun. I spend many hours searching, and I hope you will give it a try if you're interested. And if you can find my contact information somewhere, feel free to contact me. I don't want to post it here because I'm worried about the kind of emails I might get. Anyways, I hope this piqued your curiosity, and look forward to hearing more about it later on. Take care. Bye-bye.